All right, so we're good to go. So, did you get to revise this? The show in here? Did you get to go over that? You understand it? Hello? Mhm.
Yes, sir.
All right, that's good. And we essentially came to this. So we'll continue from from that particular section there. All right. Now we're gonna do another showing today. That will be the last showing. Then we revise. Let me see. All right. All right. Let's begin. Now, one of the fundamental equations in motion, right? If you will remember, is our acceleration. What is the formula for acceleration? How do we
Distance
calculate
over
acceleration?
time.
Go again. I didn't hear that.
Sorry, distance over time.
Distance over time for acceleration. That sounds like average speed to me, right? Distance over time will be average speed. How do we calculate acceleration? I remember we discussed this last class, I believe, on Monday as well.
Sorry, I changed something,
Acceleration.
sir.
Yeah, so
I'm
acceleration
changing
is equal
a,
in velocity, right? Over
a
time.
velocity over time.
So the change in velocity over time, right? And um, let me get another color, right? So this is essentially go to V, the final V. We would call that one V, or we just structure it like that. Right, so it's A2 to something like this. This would be for velocity, right? This is to differentiate between velocity and voltage. Sometimes it might mix up. So the final V minus the initial V over T. All right. Now, if we transpose for final V, right, essentially we would multiply both sides by T. So say we go ahead and multiply both sides by T, we will get AT, leaving us with V minus V0. We're transposing for final V from this equation, and then we add both sides by V0, right? So it would give us something like that, and we would have V0 plus AT. So we can use this equation now to find the velocity or the final velocity, all right, of an object if it has constant acceleration. Now, if we go ahead even further and we square both sides, right? We apply square to both sides. We square over this side and we also square over this side, right? You will be left with, and let me just switch both. It's the same thing, v squared over here, and we bring over v0 plus at squared over this side. Now, how do you remember expansion from mathematics, right? Remember expansion from mathematics? Are you hearing me?
Yes, sir.
All right. So expansion from mathematics, right? Now, if we have so this right here, this is equal to v0 plus at squared. Agreed? Right, we're just expanding them. You agree on that? Hello? Hello?
Yes, sir.
Yes, sir.
All right, so this particular v0, let's say v0 plus at squared is the same thing. All right, I'm gonna put a bracket there. It's the same thing as v0 plus at. v0 plus at. They are essentially the same thing. All right. If you are not seeing that, please let me know. Or if you don't understand, please let me know. So we're in the process of proving another equation for linear motion. That's what we're in the process of doing now. All right. So we know we proved this one last week, right? S equal v0 t minus at squared over 2. Now we'll go ahead and prove another one. All right. So you might see a question on your exam. Prove S equal v0 plus at equal at squared over 2 minus at squared over 2, right? You will start from the beginning here, from the basic equation, and you should be able to prove that. Now for this one, right, we should be able to prove another one, which we'll get to in a second. But how would you go about expanding this? What is the first step in expanding this from mathematics?
Sir, open when I bracket them.
All right, so you open the bracket. All right, what would you get?
V0 bracket V0 plus 80.
All right, so v0 bracket v0 plus at plus what else?
Plus 80 bracket V0 plus 80.
All right, what's the next step? Expand them now, right?
You'll multiply something.
Exactly. So what would you get? What would you get for this one? All right, let me start. V0 squared. All right, so you essentially multiply this by that, right? Yes or no?
Yes, sir.
And then what would you get next? What's the next thing that you would get? You
Plus
multiply
V0
V0 and
AT.
AT. Exactly. V0 AT. Let me fix that quickly. No. What would you get next over here? No, we're working with over here. Multiply that by that. How would you get?
So, are you same thing V080?
And what else?
EAT squared.
AT squared. Alright. And we could put these two together, right?
Yes, sir.
These two are the same. So we'll have V0 squared plus 2V0 AT plus AT squared. Alright. Now, if you look back on our equation, right? But let us first let's first factorize the A. That's the next step. So we take these two two elements here, and we factorize the A out of them. So V0 squared plus, and we take out the A. What would we be left with? All right, let me move this over here.
2VT.
All right, give me a second. Let me just move it. Sorry. V0 squared, and then moving this. Maybe try that next time. All right, so move this over here. Okay. And we want to take out the A. I want to take out the A. So what would you left with again? So V squared equal V0 squared plus A. Right? What would you be left with?
2VT.
2 V0 T. And plus what?
T.
Plus T, are you sure?
T squared.
T squared, what else? Isn't there something else?
Yes, sir. A.
All right, so we take out one of the A, and we have T squared here. Remember that this A was in a bracket, it's squared. All right. Now, say we also took out the 2. Let's take out this 2 as well. Right? Let's factor out that 2 as well. So V0 squared plus, I should try and differentiate the plus and the T's a little bit better. Right? The T's have a slight curve, while the plus is more straight. So the T's would have a slight curve in them. All right, to differentiate them. While the pluses are much straighter. All right, let's take out the 2 as well. So we'd have 2A. What would we have first? Let's take out this 2. What would we have first?
VT.
All right, so V0T.
V0T.
Exactly. Plus what else? Over here now.
AT square.
AT squared. We're dividing both of them by 2. All right, so what? It would just be AT squared? Would it just be AT squared, or what? What would it be?
You put divide 2 underneath it, sir.
Exactly. So AT squared over 2. No, does this look familiar? This right here? Yes or no? Right? Looks like this equation, right?
Yes, sir.
Yes, sir.
All right, so we have V0t minus AT squared. Or this should be plus. Why is this plus? This is minus. This should be plus, sorry. All right, that's a plus sign. Yeah. And then this would be S. And we fix this. All right, so this would be plus. This would be S, sir. So this is our S. So for the final equation now, so far, what do we have? V squared equal what?
V0 squared.
V0 squared, yeah, plus
2AS.
plus 2AS. All right, this is our next or second second formula for linear motion. All right, and this is how we start. So whenever you are required to do these questions, you want to remember where to start from. So for this particular one, you start from acceleration, constant acceleration. All right, and you work your way down, and you remember the different sections. For example, you should remember that we squared here. Square both sides. All right, so here you should remember that you square both sides and then you expand. All right, so you want to remember these particular sections and the important part. So anyone doesn't understand what is happening here?
Sir, why do you square both sides, sir?
All right, you square both sides to essentially expand, right? That's the only way that we can actually relate it to this particular equation. This is what we want to try and get. We want to relate the velocity or the final velocity and our acceleration and the displacement. That is the only way we can do that. All right, so it is a step in that direction, because remember the t squared here, right? If there was that, if it was just t, right, we wouldn't have to necessarily do to square both sides, but because there's a square here, we have to square everything. We can't just square one particular thing. If there was no t squared here, then we could just leave it at t. But because there's a t squared here, we have to square everything in order for us to, and then expand for us to get everything. All right. Any more questions? Please, any more questions? All right, I know this is a step up, right? You would usually just memorize these equations from CSEC, but this is not CSEC anymore. This is actually CAPE. All right, so that's how it is. Now, if we want to go ahead now and find the distance, right? We finally came to a formula that relates distance to acceleration to velocity, right? There's no other formula that does that. Now, let's put it back around here. V0 equal V0 squared plus 2AS. Now, what if we want to find S? What's the first step? What's the first step in finding S or the displacement?
Get rid of the square, sir.
All right, so get rid of the V0. Perfect. So how do you do that?
Bring it over.
All right, so bring it over, be more specific, right?
Put it beside V square.
All right, so all right, let's put it beside V squared. So tell me, what would we get? V squared. What's next? Minus V0 squared equal to AS. Are we finished?
No.
All right, what's the next step?
Divide by 2.
Divide by 2A.
All right, so V squared minus V0 squared over 2A equal S. Simple stuff. All right, so this is the displacement of a body.
No, sir.
in uniform or constant
Divide.
acceleration. I hear a question. Yeah. I hear a question. Divide. No questions? Any questions here?
No, sir.
All right. So we're good. All right.
Move, sir.
Yeah. Go ahead.
Wait, sir.
Yeah, I'm hearing you.
So we have 2AS, sir. Why didn't you just divide everything? Why did you just divide by? So why did you just divide by 2A?
On one side, like on this side alone.
Oh, yes, sir.
That's
Why
what
did
you're
you
trying to say. Oh, all right.
just divide
All right. I get what you're saying.
by
All right.
2A?
I get what you're saying. I get what you're saying. I understand what you're saying. So you would go ahead and divide both sides by 2A. Let me
Yes,
just
sir.
rewrite
But
that.
sir, why?
As you're breaking up. Are you hearing me? Anyone else hearing me? Probably it's my internet.
Sir, here, sir.
All right.
Yes,
So
sir. I hear you.
I'm not sure who that was.
It's Oshin.
Machine. Let me see. Bottleneck is off. Machine. Repeat what you were saying, please. Machine. All right. All right. Send a message in the chat then. If you're not, I don't want to move past and then it's not clear. All right. So I think she's saying that why we just did the 2A for one side. Right. So we'll just go ahead and do that then. Um. So come on. I'm tired of the red pen. It keeps on giving
Yes,
me
sir.
red pen.
I'm
Oshin?
hearing.
Alright, they're breaking up. You want to send? Let me type it. Alright. Yeah, because we wanted to find S. That's what we're trying to find. Alright, so we want to find the displacement of the body. So therefore, we divide both sides by 2A to solve for S. Alright, just for flexibility, in case a question asks you to to determine the displacement of a body undergoing constant acceleration, then you could be able to transpose. All right. Okay.
Yes, sir.
All right. Good. All right. So move on now to, let me see. All right. So a small aircraft whose speed is in the air, in still air, right? A small aircraft whose speed in still air is 200 kilometers per hour heads due north at the speed. A wind blows due east 6 kilometers per second. Carrying the aircraft off the northern direction. All right, so it basically changes the direction of the aircraft, determine the resultant velocity of the aircraft seen from the ground. All right, so this is just an example. So we have our aircraft here, and it's heading north at 200, right? Whenever we start a question, you want to draw diagrams to get an understanding of what is happening. And there's a wind that blows east, right? So essentially, you have the velocity here moving in this direction, and then you have another velocity here moving in this direction, right? Velocity of the wind. So it's moving in 60. I'm sure this should be 60 kilometers per hour. I am sure I don't have the book close to me, but I think that should be 60 kilometers per hour. Right. Yeah. So all right, let's work this question. No, we're gonna start with the x direction. Let's begin with the x direction. Now, velocity in the x direction. You will first look on VW, which would be our wind. Let's draw a diagram showing that velocity of the wind, VW, and we have of course, a y component, Vy, and an x component, Vx. All right, so how would we determine our VWX? Sorry, VWX, VWY. Now, how would you determine now the velocity of the wind in the x direction? What should we use? Sine, cos, or tan?
Tan, sir.
Oh, it heads east. Sorry, my apologies. What am I thinking? Sorry. It heads east. Not at an angle. East. Alright, so you have VW in this direction. Now, in the x direction, we have VW. Right. VW. And in the y direction, we have the velocity of the aircraft. We have the velocity of the aircraft would be, let's call it VA and VW. All right. How do you calculate now the resultant velocity? How do you do that? We have, let's draw our graph here. We have VA in this direction and VW in this direction. Which one of these, let's say A, B, C, D, which one of these would be in the resultant velocity? Where would that particular thing be? The resultant velocity, A, B, C, or D?
A, sir.
All right, so that would be in A. So let's draw A. That is to show the resultant velocity. So we call it VR. Now, to find VR, I want to find VR, velocity, resultant velocity. How do you go about doing that?
VA square plus.
Go again. Your mic is low. I am not here. Hello? How do we calculate VR? What's the first step in calculating VR? All right, we spoke about this already.
Sir, VA square plus VW square.
All right, so VR is equal to what?
VA square plus VW square.
Are you sure?
No, Max.
All right, this is Pythagoras. Pythagoras, and you're forgetting the square. All right, you're forgetting the square here. Don't forget the square. All right, so VA is how much? What is the speed of the aircraft?
200.
200 kilometer per hour.
All right, so 200 squared, and VW is how much?
60.
60
60
kilometers.
per hour.
All right, what do we get here? 200 squared is how much?
Um, 40,000.
40.
And 60 squared?
$3,600.
All right, and VR squared is equal to, what's the total?
What is 3,600?
All right, and VR would be?
The square root.
Which would be?
I don't know.
Yeah, that's it. All right, so VR squared, let's say VR would be the square root of 43,600, which would be
208.8.
208.8. No, this question didn't necessarily ask you for it, but I feel like I want to ask you for the direction in comparison to the x-axis, of course. How do you calculate that? Which one will we use? Sine, cos, or tan?
Cos, sir.
Cos? All right.
So the tan.
Make up your mind. Which one?
Sine, sir.
All right. So here's sine. So it's so like
Yeah,
I guess
cos.
it. All right. That's wrong.
Sir, anyone, sir,
Right.
use cos.
That's wrong. Well, we could use any of them. Yeah, because they have the value of any of them. All right. So we could use adjacent, and we could use hypotenuse, and we could use also opposite. But the safest way, I would say to use tan for me. All right. So as I said, the easiest way could be use, we could use either of them, but the easiest way is opposite and adjacent because they gave us these values. Remember, or the safest way then. Remember, we calculated this, and this calculation could be wrong, right? And it could jeopardize. Say we're in a rush, it could jeopardize our last result. So the easiest and the most, the safest way, I would say we use tan. All right, so tan theta is equal to what exactly?
The opposite of adjacent.
All right, so you're not wrong if you said cos, you're not wrong if you said sine, you're not wrong. But you understand what I'm trying to say, right?
Yes, sir.
All right.
Yes,
All right. What is our opposite?
Hold on. 200, sir?
32, yeah.
No, hold on.
200 over
over
200.
60.
Over 60.
60.
All right. And what do we get here?
Uh-huh.
What do we get? 200 divided by 60.
16. So the
60?
20, a
3
two,
point only
like,
by
cause
3.
of 10,
3
3.33
point
Okay.
recording.
3
All
yeah,
right. So 3.33.
3.33
And
continuous
how
3.
would we, when would we, how would we calculate the angle? So what would the
So
angle be?
me think you go do an inverse something.
All right. So
Yes,
inverse
sir.
tan. And what do we get?
73.3.
Degrees.
All right. That's good. All right. So anyone not clear? Right? Anyone doesn't understand what's going on here? All right. So I take it that everyone is good. Okay. No, it's the same thing, right? This is the same setup. All right, I think this is the same setup. We'll just move on. All right, so we'll go to the summary now. So, summary on displacement time graphs. A body traveling with uniform velocity covers equal distances in equal times. Its distance time graph is a straight line, of course, like OL in the figure below for a velocity of 10 meters per second. So the slope of the gradient of the graph M LM divided by OM, that should be equal to 40, right? We're just finding the gradient. Um, yeah, just finding the gradient or comparing these 2 points. 40 divided by 4, that should give us 10 meters per second, which is the value of the velocity. So in conclusion, the slope of a gradient of a displacement time graph represents the velocity of the body. And we said that if we had a, what if we had a, this is a displacement, this distance, and we have time down here. What if we had this curve here? What would that indicate?
It's not constant.
All right, so what's not constant?
Speed. What do
All
I
right,
don't
so
know?
the velocity is not constant, right? Which would suggest,
But it's accelerating.
all right, so this is suggesting that it's acceleration, that it's accelerating. Now, if we wanted to find acceleration, now if we wanted to find the instant velocity, instantaneous velocity, how would you do that again?
Use a tangent, sir.
Exactly, so you put a tangent to the curve right here, or whatever, or wherever, right? I'm not able to get a tangent perfectly. I don't think so. Oh yeah, what are you doing? Let me try. So if it says, say this is 0, this is 1, this is 2, this is 3, and this is 4. If you wanted to find the instantaneous velocity at 3, you would essentially bring it up to the line, and then you draw a tangent to that particular line. Let me see. Yeah. And then what would you do next? After you find the tangent, or after you establish tangent, what do you do next? Hmm?
So I use it to find the gradient.
All right, so you use a tangent to find, you essentially find the gradient of, perfect. Find the gradient of your slope. Instant day. Oh my god. Instant. Please be patient with me. Instantaneous velocity at 30 seconds. 30 seconds. All right. Yeah, that's essentially it. Tangent to a circle, tangent. All right, this is just to ensure that we understand tangent and that it is perpendicular to the radius at that particular point in contact. Yeah, see another tangent here, and we find the slope. Just like some examples of tangent. Another example of tangent. So as I said, this curve graph is suggesting acceleration. And if you wanted to find the instantaneous velocity at this point, you would do that there. All right, now to the nice stuff, right? I want you to tell me what is happening from A to B. What is happening from A to B? When the objects move from A to B, what is happening?
So speed or whatever is
Acceleration.
increasing.
All right, that's good.
Acceleration.
It's going up, accelerating. That's what they call
Acceleration.
it. Yes.
Yes, acceleration. What is happening today? Acceleration from B to C.
The same thing, sir.
Constant, sir. The constant speed.
All right, so we see constant what? Constant acceleration, constant what?
Acceleration.
No. That's not constant acceleration.
Sorry, it's just
Is
constant.
it this
Sir, the speed.
constant what?
Sorry, speed.
What is
Speed,
constant?
sir, velocity,
Exactly, so
something.
speed. All right, so it's constant velocity. Perfect. From C to D.
Sir, it's going
like
down. It's
It
falling.
decrease.
What is
Accelerating
what is the
down,
decreasing?
something like that.
And what do you call that word?
Its speed is decreasing. Or accelerate. We don't know, sir.
What's the name of that word?
Right.
What's that word?
Accelerate. We don't know. Acceleration, decreasing.
D.
We don't know.
D
Speed.
say.
Displacement.
This
Sir, repeat.
Acceleration.
Acceleration, deceleration.
deceleration. Am I spelling this correctly?
Oh,
Please tell me.
deceleration.
Yeah, deceleration. All right, so you made a good attempt. Right. Decelerate. Oh my God. What is
Sure, that wrong, sir.
Listen, I got one in English, all right? Just so you know. I got one in English, and I haven't done English since. Just straight physics. Deceleration. All right? Is that correct?
Just
It looks correct. Don't Google it, all right? You got the exam, don't Google it. You should know this. All right, what is happening
Sir, I
from D
think
to
I
E?
want C though.
1C? Oh my God.
sir, doesn't physics require English, sir?
Are you talking about your teacher, young lady?
No, sir.
Oh yeah, there's 1C, just 1C. Just 1C. Yeah. Alright, so I was just testing you, right? You are ready for your English exam as well, right? Yeah, so deceleration.
Wow.
D to E. What is happening there?
Constant velocity or whatever. Yeah.
Are you sure? But we said B to C is constant velocity.
What we had to sir? B to E, D to E.
D to E.
Is a displacement time graph. Is the displacement changing? Let's say this is at 5 meters. Is it moving from 5 meters? Constant what?
But sir, that constant.
What is constant in this case?
Sir, right speed, sir.
But we said it is constant speed at B2C
Speed.
as well.
Oh,
Is it moving from 5 meters?
No.
Isn't it
no, no,
still
no,
at?
sir.
So what does that mean?
Sir, is
So
the
this is 3 seconds
constant
and this is five
no
seconds.
acceleration?
It's not accelerating. All right, think about the logics. You increase acceleration, go from A to B, acceleration. Then from B to C, constant velocity. And then C to D, deceleration. D to E will be what in real life?
Constant deceleration, sir.
Uh-huh.
Constant deceleration.
Constant acceleration? No, because it was decelerating at C to D.
Sir, deceleration, me say, sir.
Yeah, we said this deceleration for C to D. No, for D to E, and it's at 5 meters here. Is it moving from 5 meters as the time changes?
No, sir.
So what is the object doing? Is it moving or not moving?
Not moving.
Exactly. The object is not moving because as time continues, it is still at 5 meters. That clear?
Yes, sir.
Yes, sir. So
Yes,
wind
sir.
up.
So velocity is at 0. It's not moving.
Sir, not moving.
Object not moving.
So, sir,
That's possible in
Okay.
real life.
So, sir,
Isn't that so?
sir, so you want instance, sir?
You go from school to Trelawney, right? You go from school to Trelawney. You increase in speed.
Sir,
I go from school
what
to
school at
Falmouth.
Chiladi?
I know. All right. So you go from, and that's why I said Falmouth. That's why I changed it to Falmouth. Right? You go from school to Falmouth, A to B. You increase in velocity. Why are you laughing? Focus, right? Focus, right? You're going, you're going from A to B, and you increase in velocity. Say you're moving towards the highway now. You're moving towards the highway, and the highway is a smooth road, right? So you're moving at a constant velocity here from B to C. Then at C to D now, you're going to stop at where would you stop? You're stopping at Juicy Patties, right? You're stopping at Juicy Patties,
Sir, that
so
even
therefore
upon
you
a wheel.
slow down. Oh God, that's not even the point. All right, you're stopping at Tasties. All right, you don't stop at Tasties. All right, you stop at Tasties, right? You slow down, so you decelerate, and then from D to E, you're at Tasties, and you're not moving, right? You're not moving from D to E. You're stuck at Tasties, so your velocity is 0, object not moving. All right, is that better? Is that better?
All right, sir. So what happened from E
Yes,
to
sir.
F now?
All right, so E to
Yes,
F. What
sir.
happens
Yes,
at E
sir.
to F now?
Then, sir, it start decelerate again. And they go down.
Let's go to that one. It's displacement. All right, so you're at 0. You can't decelerate any further than 0.
Exactly.
So if you're not decelerating, what would you do?
So if you're not decelerate, you have to accelerate. And if you
Exactly.
accelerate,
But
the graph will go up.
Not necessarily, because this is at school, and this is essentially Trelawney, or sorry, Falmouth. This is Falmouth, right? So what are you doing here? And what are you doing here? From E to G, what are you doing?
Sir, I don't know. So if you stop and move off again, then I accelerate again.
Yes, he's accelerating again, but He's going from Falmouth to where?
School.
Exactly. So it's going from Falmouth to school, back in the original direction.
Sir, it just go pick up
So
speed.
exactly, it's picking up speed from E to F. So E to F is acceleration, but in the opposite direction. All right, so here we are in the opposite direction. We're going back to where we began. Remember we did the exercise, right? Where we had say this one here, right? And we had something like A, B, C, right? And then we had a straight line, right? From and then this is D. Let's call this X. So the total distance would be what? What would the total distance be?
A, B, C, D.
Exactly. A, B, C, D. Now look on this one. That's not what I wanted to show you. Forget this one. That's not what I'm just realizing. No, that's not what I want to show you. Come on. Remember, we established this from the beginning. Where, oh, God. Come on. Alright, don't pay that anymore. Alright, and we had A, B, C, and this is a B, C, D, right? And the object move in this direction. So what would the total distance be? It goes from A to B, then B to C, then C to D, and then
C
A
to
to
D.
then D to A. So what would the total distance be?
A, B, C, D.
Exactly.
And back
And
to A.
here, DA. What would the displacement be?
0.
Exactly.
Zero.
So the displacement would be 0. So essentially, you're going from school to Falmouth. In this section here, you would be going from Falmouth to school. The reason why it looks like this curve here, is because it's accelerating, but it's only doing it in the opposite direction. This curve. All right. So what is happening from F to G? What is the velocity?
Constant.
All right, so constant velocity again. All right, and from G to H, what is the value of the velocity? What is the velocity there from G to H? Is it changing? Is it 0? Is it what? What does that mean?
Sir, it will go change right there, so right.
It changing? Are you sure from G to H?
No, sir, it's not
It
changing.
look constant.
No,
Alright, so
sir,
constant
stay
velocity as
same.
well.
It stays same.
All right, but where is beyond school, right? I know you have Falmouth. I'm not from Trelawney, right? I know you have Falmouth and school. Where is beyond school? Give me another community.
Sir, Martha Bray.
All right, I think school is at Martha Bray, but I'll work with that.
It has Zion, sir. Its school is at Zion.
All right, so Zion. All right, so Zion here. So basically, you go from school. You're at school, but you're going to pick up some food from Juicy Patty. So you go to Juicy Patty in Falmouth, and then you go to home. So let's say home is in Zion. All right, what is HI? What is HI? What is the value for HI? The velocity. What is happening there?
It might decelerate.
Sir,
All right, so
yes, sir.
all right, so deceleration again. 1C. Acceleration. And what is happening from I to what is happening at I?
Him stop at I.
All right, so it stops at I for
This
a few more
stuff.
seconds, right? For 0. So all right, so it stops, and he realized that he left something at school. So what did he have to do?
Go
He
back
had
to
to go
school.
back, right? Exactly.
So
So
I
what is
accelerate
happening?
again.
Acceleration, I to J, acceleration. Mhm. Acceleration. And then from J to K, what is happening? J to K, what is that?
You might decelerate
Exactly. So he's decelerating back to 0 again.
at K.
All right. So are we clear? Anyone doesn't understand what is happening? Or doesn't understand one of the steps? Want me to go over it again? One of the steps. All right. No. Yes. All right. Move on to the next graph. Now, this is a velocity time graph. Now, this is a little different, right? But essentially, let's see how it goes. All right. Now, what's happening from A to B again?
Acceleration.
All right.
Acceleration.
Acceleration. And from B to C?
Deceleration.
All right. Are we all seeing that? Anyone doesn't see deceleration? Anyone doesn't see it? All right. And what is happening from C to D?
Stop.
Are you sure?
So it's not moving.
No.
Is it
Are you
not
sure?
moving? Are you constant?
Already this time constant.
All right. So you see the
Yes.
difference, right? You see the difference. So it is still at 5 meters per second. All right. It's not changing. All right. I know it's not exactly at 5 here, but you get the point. 5 meters per second. And from D to E, what is that?
It might decelerate rapidly.
All right. So rapid deceleration, right? Rapid. So he was driving, and the police came out and essentially put out his hand, right, and he had to stop the deceleration. So that's from D to E. All right, next E to F.
Sir, in a move none
stop.
time.
Nah, move. Mm-hmm.
All right, so V is equal to 0, E to F, and F to G.
Just a pick up speed, sir.
Sir, man, I know what I'm going to say.
Go again.
So, just a pick up speed, like. So like in just a pick up speed.
All right, yeah. So pick up speed. What we call it? What we call it in physics, right?
Accelerate.
Acceleration.
All right, we can't say pick up
Acceleration.
speed. V minus V0 over T. Right? We can't say that. But that's fine. Okay. Acceleration. From F to G. Alright, and from G to H.
So that like he stop again, man. or constant? Sir,
You
is
stop
that
again? Hmm?
Sir, that constant.
constant or
Alright.
typing stuff again?
Constant.
Constant velocity, right?
Constant, man.
Yeah, so G to H. So this would be in the opposite direction, of course. Alright. And what is that from H to I?
Acceleration.
Alright, so
Sir, speed gone up, accelerating.
acceleration. R. Hmm. Are you sure about that? Think about it again.
Front. Uh,
Say this is 5 meters per negative 5 meters per second now. Think about
So
it
like
again.
this.
All right, so I hear that.
I'm gonna say Oshina say it. Oshin say it on.
I didn't hear that.
Decelerating, sir. It's
All right.
deceleration.
So
Is it?
deceleration. So it's essentially going back to zero, right? From H to I. All right. Are we clear on this?
Yes, sir.
Yes,
All right.
sir.
So I am pleased.
Yes, sir.
All right. So we move now to what is this? No. Move now to our next topic for today. Let me see. Where is it? All right. So the next topic is dynamics, right? We will stop at let's stop at 2:30 for today. Let's just finish these few slides. All right. Give me a second. Let me go for my charger. All right, let's go again. So, all right, go ahead, Jadon.
Sir, mistake, sir.
Okay. All right, so we now move to dynamics, right? And this is the branch of mechanics concerned with forces that change or produce. This is actually for next week, right? We finished this week's topic on kinematics, but we'll just start. I was preparing this one next week, right? But since we are finished with kinematics, as you can see, this PowerPoint is not necessarily completed, but because we finished everything that we have to do today and for this week, we'll start. All right, so dynamics, the branch of mechanics concerned with the forces that change or produce the motion of bodies. So for centuries, the problem of motion and the causes of motion, right, had puzzled scientists. Right, it was not until the time of Galileo and Newton that real progress in its explanation was made. So it was thought that a force was needed to keep a body moving, and that if this force was somehow removed, right, immediately the body would come back to rest. But then Galileo in 15, who died in 1642, proposed that a force was only needed to change the state of motion, thus laying the foundation for Newton's three laws and, of course, his other work as well. So, let's look at this example. The object shown in figure below, starting from a rest point at A, slides down a frictionless slope. All right. Let me get something and come back. Sorry, give me one more second. All right. Yes. All right. Yeah. So, are you hearing me?
Yes,
Yes,
sir.
sir.
All right. So the object shown in figure below, starting from rest point at A, right? It starts up here. Starts up here. We have different slopes for it to go up. All right. So when the object is released, it will slide down the slope and go up the opposite side to the same height. Right. Now this would be if it is placed at an angle. If the slope, of course, or the whole trajectory is frictionless. All right, so you'll find that it will move to the same height, because of course, energy must be conserved. All right, so it will gain kinetic energy down here. Right, let's say it didn't have any collisions here. Let's say it just flowed freely with no friction or anything. The energy must be conserved, so it should go back up to the original height. Kinetic energy down, potential energy up. Kinetic energy down, potential energy up. So if we decrease the angle of the slope on the right hand, then the object will move further, or it will have a hard time, or you'd have to go through more distance to reach back up to its original position, but essentially it should. All right. Now, if we were to reduce the slope to 0, then theoretically the object would go on forever. This is therefore because no force is being applied. Remember the trajectory or the
Frictionless.
yeah, the plane is frictionless. So we will say that the resultant forces on the object will be zero. So this therefore shows that the force is needed to change the motion of an object. So experiments where there's no resultant force are difficult to achieve in real time, since frictional forces always affect the result. In 1687, however, Sir Isaac Newton published the Mathematical Principles of Natural Science, in which he stated three laws on which the science of mechanics is based. All right, and we said the first law, a body, right? You should have been introduced to this already from CSEC, from the CSEC level. A body at rest will remain at rest, and a body in motion will continue in motion at a constant velocity unless acted on by some unbalanced external force. So this ball is said to act in this direction, right? If we have the body moving in this way, what is the force acting on the body currently? What is the force causing the body to act in this way?
Uh, Gravity.
Exactly. So gravity is acting in this direction, right? And it is the one. It is causing the object to move in this particular direction. So because gravity is acting downwards, and we have another force acting, we don't want to go to detail into this as yet, but you have a force exerted by the plane, right? That is causing the object to roll down instead of falling straight down. So gravity is the only one that's causing the object to move in this way, and essentially it goes up to this particular point. As you said, energy is conserved, so the same height that it was before, gain kinetic energy, it should reach back up to its original position. Now what's the force acting in this direction again? What is that same force that would cause it to come
The
down?
same gravity.
Exactly. So um that's what we would get. So unless there is another force, right? In this case, in this particular case, with the plane or the angle of the frictionless area, right down here, unless it's an external force, you will observe that the object will gain energy here and it will continue moving in this particular direction forever, unless another external force begins to act on it. All right. Newton's second law, on the other hand, says that if an unbalanced external force F causes acts on a body, M, right, it will give that body an acceleration A. Right, so let me say it again. If an unbalanced external force F acts on a body of mass M, it will give that body an acceleration of A. The acceleration is directly proportional to the applied force and inversely proportional to the mass of that particular object. So that relationship, right, because A is directly proportional to F, right, you'd have F equal A, and then it is inversely proportional to the mass, right? Therefore, you should get a relationship looking like this. And remember, all of these are vector quantities, except the M. Of course, M is not a vector quantity. Sorry. Yeah. So you have all of these as vector quantities. And then if we transpose for the force, the unbalanced external force, we should get F equal M A. So the same direction that the acceleration or the force is being acted, that or external force, that should be the same direction of our acceleration because they're both directly proportional. All right, so that is it for this week. We will continue dynamics next week. All right, we'll continue that.
Yes, sir.
All
Yes,
right,
sir.
so
Yes, sir.
all the best, everyone.
Is there?
All the best.
How for that?
You ain't leaving.